So far we've looked at classical entropies and related the idea of entropy with information. So if I have an event A with outcomes given by a set of AIs, I would know that the entropy or information associated with that event is going to be given by the negative of the sum of probabilities AI log to the base 2 of PAI. And this would give me the probability in units of bits. Sorry, the entropy in units of bits. This is the entropy, also called the Shannon entropy. It's a concave function. It also represents the amount of information that is present in the event A. And the amount of information means how much do you not know about A before you are measuring it. That's the uncertainty in A before you're measuring it. Once you've measured A, of course, if the information content is higher, it means you know more. But prior to measurement, the information really means you're uncertain, you're in the dark about that event. Right? So higher information content of an event means you're more in the dark of that event. So now let's try to take this idea of Shannon and try, which is a classical idea, and try to come up with, propose a definition that works for quantum states. So we would like to come up with this, or propose the idea of a quantum entropy associated with a density operator. And that entropy is, of course, again represented by the letter S, like any other entropy. And now we define the entropy for a density operator, rho, which could be a pure or a mixed quantum state. And this is defined as negative of the trace of rho log of rho. So this is called the von Neumann entropy of a density operator of a quantum state. It's the quantum analog of Shannon's entropy. Again, its units are, if you're using log 2, the units are bits. If you're using log, natural log, the units are called nats, natural units. If you're using log to the base 2, the units are generally called bits. Now, first of all, this is a number because you're taking the trace. It's just a scalar. This is a density operator, so you take traces of matrices. So this is a matrix, of course. This again is a matrix. The log of a matrix is defined in a special fashion. Now, since rho is a density operator, it must be Hermitian. Hermitian means its eigenvalues are real. And in fact, you know that its eigenvalues have to be positive as well because it's a positive operator as well. So the eigenvalues are real and they're positive. Any such matrix can be diagonalized. So if we were to write down the diagonal matrix associated with rho, this is just a matrix in which only the eigenvalues populate the diagonal. So from rho, we can easily find the diagonal matrix through a sequence of operations which goes as the following. This is the general way in which you would diagonalize a matrix. So you take a matrix and form a matrix of the eigenvectors of rho. So the columns of this matrix are the eigenvectors of rho, and this is just the inverse of this matrix. Okay? In this manner you will get a diagonal matrix. This is something you learn from basic linear algebra. This also means that Rho is D. I think there's an inverse here, but it doesn't matter. So rho can also be written in terms of the diagonal matrix. Okay. So if you would like to find out the log of a matrix rho, what you would do is you would just take V inverse and put in the log of D in between the matrix of eigenvectors and its inverse. So you just take a diagonal matrix and find the log of all the elements of the diagonal matrix and sandwich it in between the matrices of eigenvectors. So this is how you can find out the log of a density operator. You find out the associated diagonal matrix, which is the matrix of eigenvalues. Find the log of each element in the diagonal, put the log in the diagonal, and sandwich this matrix in between the matrix of eigenvectors and the inverse of eigenvectors. This is how you are able to find the log of a matrix. Now another operational definition of this entropy goes as follows. Since rho is a density operator, it must be diagonalizable. So I can write down the spectral decomposition of this matrix, which means I can write down rho as the eigenvalues. Let's call those eigenvalues rho m, followed by ket m bra m summed over all m's, right? Any density matrix can be written in this form. The spectral decomposition of a density matrix. Yes?
So can you tell how written log rho is equal to 0?
So I'm explaining here how do we find out the log of a density operator. In order to find out the log of a density operator, I just find out the diagonal matrix. So there's a proof for this as well. You can look this up in any linear algebra book. So the log of a density operator is the log of a diagonal matrix. The log of a diagonal matrix is just a diagonal matrix in which the entries are the logs of the individual elements. And you sandwich this matrix between V and V inverse. So look this up in a linear algebra book, please. Now, do you understand the spectral decomposition of a density operator? Right? So it's a Hermitian operator. Any Hermitian operator can be written in this fashion. These are the eigenvalues of the density operator, and since it's a density operator, these are positive values because they correspond to probabilities. Remember from our previous lectures, this rho m is a value which is the trace of the product of this outer product with rho. So it's a probability. This you learn from basic quantum mechanics, and I think we spent one lecture on this already. Anyway, any density operator can be written in this form. Correct? In other words, a density operator, if I were to represent this in matrix form, this would mean rho 1, rho 2, rho 3, all the way up to rho d, where d is the dimensionality of this density operator, and zeros everywhere else. So it's a diagonal matrix with rho 1, rho 2, rho 3 in its diagonal and as diagonal entries, which are the eigenvalues of rho. Right? So this is just a compact way of this matrix representation. So now what I'm trying to do, I'm trying to look at this definition of the von Neumann entropy and come up with an operational definition of this entropy. Operational means something that you can compute on a computer or on a piece of paper easily. So if I were to write down rho log of rho. This would mean rho is this sum over m, rho m, ket m, bra m. Remember, this is an eigenvalue, an element. Log of let's choose another index k, rho k, ket k, bra k. Now this is a diagonal matrix with elements rho k. So how do you find the log of a diagonal matrix? You just take the logs of the diagonal elements. So I can combine these two sigmas, sum over m and k, rho m, log of rho k, correct? And the two outer products, ket m, bra m, ket k, bra k. Alright. Now what I could do, I know that this is a Kronecker delta between m and k. It's non-zero only when m equals k. So one of this thing goes away and I'm left with the sum over m, rho m, log of m, and ket m, bra m. Correct? Now remember, this is a probability or an eigenvalue, this is another probability. Now if I were to take the trace of this thing, I need the trace, the von Neumann entropy becomes minus the trace of this object Now the trace of an outer product, the ket followed by a bra becomes the bra followed by the ket. And this is just 1. So I'm really left with minus sum over m, rho m, log of rho m. So this is an eigenvalue, it's a probability, another eigenvalue which is a probability, log. And look at the similarity of this relationship with h of some event, a probability of ai, log of probability of ai. Aren't the two very similar? They're just identical. Hence, the definition that we invoke for the von Neumann entropy is quite an apt definition. It captures the entropy of a quantum state. If I have a pure state, okay, so I will give you half a minute for this to sink in. The definition of a von Neumann entropy is given by minus trace of rho, log of rho. Operationally, this means minus sum of over the eigenvalues of log rho I. This is how we define von Neumann entropy for a quantum state. Exactly similar to the classical definition. Minus to make the function concave, sum over probability multiplied by the log of that probability. Independent of the value, it only depends upon the probabilities. So a probability distribution has an entropy. A density matrix is a probability distribution, hence it has an entropy. If I had a pure quantum state, and I were to diagonalize it, what would the density matrix look like for a pure quantum state? No, Identity is a maximally mixed state. It's not a pure quantum state. So I take any row pure and I diagonalize it, make it into a D. What will this matrix look like? Oh, zeros everywhere?
No, off diagonals.
And what's in the diagonals?
Um,
One non-zero entry in the diagonal.
Sorry?
Well, one non-zero entry in the diagonals, all else will be zero.
Right. And what will be that non-zero thing?
That will be 1.
1. Right? So it will have 1 here. Everywhere else there will be zeros. That's the density matrix in diagonal form of a pure quantum state. You take any pure quantum state, you can always diagonalize it, and at the end it will look like this. So what are its eigenvalues? There is only one non-zero eigenvalue, which is 1, and all the rest are 0. Right? Like a probability distribution function that just has a drag delta at one value. That's what a pure quantum state is. So what's the, if I were to apply this formula over here, and I would use this definition, 0 log of 0 is 0, and this is a problem in homework number 4 as well, so you have to prove this. If I were to use this definition, what would be the entropy of a pure quantum state? Zero. A pure quantum state will have entropy 0. For a pure quantum state, the entropy is 0, just like a probability density function which is certain at one value and 0 elsewhere. And if I had a maximally mixed density matrix, this means that the diagonal element, so what will be the density matrix in diagonal form? In shorthand, I am just writing this as diagonal. What will be the density matrix for a maximally mixed state? Suppose it's a matrix of size d by d, or 2n by 2n. So what will each element be? Maximally mixed, maximal randomization. 1 over d in each point, right? So there will be 1 over d here, followed by 1 over d, and 1 over d is all the way. And the entropy of this state, just apply the formula here, these are the eigenvalues for this density matrix, it will be log b. That's the maximal entropy of a maximally mixed state. In fact, you can prove this using the idea of Lagrange multipliers, and I've included one question in homework number 4 to this effect. Pure quantum state is at one side of the spectrum, entropy 0. Maximally mixed quantum state, entropy maximal. Disorder in naive terms is maximal. The uncertainty is maximal. It harbors maximum information because there is so much to be learned about it in a measurement. Right? So this is how we define the entropy for quantum states. Now, another really nice idea is that of an equilibrium density matrix. Any questions for this? So now I would like to come up with the idea of an equilibrium density matrix. You might have seen this in statistical mechanics if you're physics students. Now, I want you to ask is, when something is in equilibrium, what does the second law of thermodynamics dictate? What about its entropy? It can never decrease. So you have a system and it has stabilized into its equilibrium state. What can you say of the entropy of that system? It's maximal, right? So the maximization of entropy, systems are driven towards the maximization of entropy. And when equilibrium has been established, entropy has gone up. Right? So you get into a macro state which has maximum number of microstates in it. Now what we would like to show is that if I have this entropy here, in a state of equilibrium, the entropy is maximum. So what is the density matrix when the equilibrium is maximum? We would like to find that out. But there are other constraints as well. One constraint is that the trace of rho must be 1. You cannot have an arbitrary density matrix. This is one constraint. Another constraint is that if I were to take the trace of the product of the density matrix, the equilibrium density matrix, and the Hamiltonian, this would give me the average energy of the system. The entropy will of course depend upon the energy as well. So I have these two constraints. I want to maximize the entropy with these constraints. So I can use the idea of Lagrange multipliers. How do I do that? I do that in the following fashion. I form a function S of rho which I want to maximize, or maximize this function, which means I want to find the extremum of another function, and that other function is formed by adding the constraints to this. So S of rho plus a Lagrange multiplier lambda, and one of these constraints goes in here as 1 minus trace of rho right, plus the other constraint with another Lagrange multiplier, E minus trace of rho h. And if I were to form the differential of this function, this must be 0. So I would like to find out the rho that does that. So I treat my rho as a variable and find the differential of this function and put it equal to 0. That will give me an equilibrium density matrix. So let's see how we can do that. Some nice mathematical physics at play here. So if I were to do that, then let's just first of all put in minus trace of rho log rho. I'm not going to put in the hats all the time. Lambda 1 minus trace of rho plus beta average energy minus the trace of rho h minus trace, now the derivative of this with respect to rho, log of rho plus identity. So rho into 1 over rho. The derivative of log is 1 over rho, right? Plus lambda, this is 0, minus trace identity, plus this is 0, so I get minus beta trace of h. H is fixed, it's the Hamiltonian. The derivative of this, so I put d rho and I put this equal to 0. Now this is 0 only when what I've written in the big big brackets is 0. And this happens when minus log of rho minus identity minus lambda minus beta trace of h minus beta h is 0. So the trace of something is 0 only when that something is 0. So this is what this turns out as. So log of rho is minus 1 plus lambda minus beta h. Let me reintroduce the hats. This means that my rho in equilibrium, which is maximizing this entropy, is given by e raised to power minus 1 plus lambda e minus beta h. This is the equilibrium density matrix, in which one of my unknowns is this Lagrange multiplier lambda, the other unknown is beta. So I can find out both of these constants using other constraints. So one constraint I can simply use is the trace of rho must be 1. So if I were to take the trace of this must give me 1. Right? So if I were to take the trace of this thing must be 1. This is just a number. This is a matrix in fact, because this is an identity, but all of the numbers in the diagonal are identical. Each one of those numbers is e minus 1 plus lambda. So I just take this here and put trace of e minus beta h. This will give me e minus 1 plus lambda will be equal to 1 over trace of e minus beta h. So I can just eliminate this factor over here. I put this back in here, and I'm left with the equilibrium density matrix as e minus beta h divided by trace of e minus beta h. This, as you very well know, is the equilibrium density matrix, isn't it? You can also express this as e minus beta h over the partition function. This is the partition function. So this equilibrium density matrix maximizes the entropy, this object over here. Now it's an extremum. Now you would like to ask whether it's a maximum or a minimum. The extremum includes maximum and the minimum. Minimum we know is 0. So this extremum is the other extremum. It's the maximum. This equilibrium density matrix maximizes the entropy of quantum state. That's why it's called the equilibrium density matrix. So given any Hamiltonian, if a system is sitting in a Hamiltonian, this is how you will find out what the equilibrium state is going to look like. And from this you can predict what the probabilities are going to look like. So we know from statistical mechanics and that the eigenvalues of this density operator, let's call them rho I, are just going to be e minus beta ei, the ith eigenvalue of this Hamiltonian divided by the partition function. So these are just the probabilities. Okay. This is also called the Maxwell-Boltzmann distribution. So the Lagrange multiplier technique, or the maximization of entropy, quantum entropy, also sinks in very nicely with the idea of thermodynamics. That's why this definition of Shannon entropy is plausible. The definition of von Neumann entropy is plausible. Both of them are interrelated. It's all making perfect sense. There's nothing just out of the world here. Now another, you might also ask me, how do I find out this beta here? This is the second Lagrange multiplier. So any idea how I could do that? I will have to use some other concept from thermodynamics. So can you just come up with an argument of how I can find beta? They want to check your GRE skills. So what are the units of entropy in thermodynamics? Units of entropy. Joules per Kelvin. Good. So what are the units over here? S, the von Neumann entropy. It's unitless. It's dimensionless at the moment because these are just probabilities. Bits is just for our satisfaction, but it's really unitless. Now, if I were to impart units to this, I just need to multiply it with the Boltzmann constant Kb to get the thermodynamic entropy of a quantum state. So if I were to take this quantum entropy S rho and multiply it with the Boltzmann constant, which has units of joules per Kelvin, I will get thermodynamic entropy of this quantum state. S thermal, right? And then what I could do, I could use this relationship between temperature and entropy, that is the derivative of the thermal entropy with respect to temperature is 1 over temperature, the derivative of the average energy with respect to the temperature. And from this I can get a chance of finding what the beta is. So remember, this is how we define entropy. In your basic first year physics freshman books, you might have come across S equals E over T or something of this kind, energy over temperature. This is quite a naive definition, but this is the real definition of entropy. The rate of change of entropy with temperature equals 1 over the temperature multiplied by how the average energy changes with temperature. So now if I were to find out this thermodynamic entropy and find its derivative with respect to T, then I will actually find out what beta is going to look like. So let me get you started on this. So my thermodynamic entropy is simply minus Kb rho I log of rho I. Now minus Kb log of, now rho I is really E minus beta EI over Z, correct? Correct? So I am replacing this rho I log inside the log, this probability by what I have over here, which I get from the equilibrium density matrix. Now remember, this is an eigenvalue of the Hamiltonian. Now all of this is basic quantum mechanics, statistical mechanics at work here. Now what I could do next is write this as minus Kb log of E minus beta EI minus log of Z. Okay. In fact, I could use natural logs here as well, because natural and The other kind of logs are just related by a factor, natural log of 2. Now, if for the time being I just ignore this kind of technicality, this becomes minus kb rho I log of e raised to minus something is minus beta ei, the exponent is written over here, plus kb rho I log of z. Plus kb beta. Now what is this thing over here? This is a probability and this is the energy in the ith state. The probability of the ith state, energy of the ith state summed over all i's will give me the average energy. Now there is no I over here, this is just a trace here, trace of E minus beta A. So this is just a number. The sum of all these probabilities must be 1. So I am left with kb log of z. This is my thermodynamic entropy in the state rho. Okay? By the way, this is also called, if you remember your statistical mechanics, this part is also called the Helmholtz function, kb natural log z. So all of this is connected together. It's all a giant synthesis at work over here. Everything is united. Entropy का उर्दू में तर्जुमा फैलाओ, मैं ऐसे ही करूँगा. Now what I could do, I need to find the derivative of this with respect to the temperature G. ये वाली, ये यहाँ से. This is the probability of the ith state and the ith energy. This is the expectation value of the energy, right? The average value of the energy. यहाँ से है. Now let's take the derivative of this. Let's look at the left hand side of the equation that I have written in a box. Let's find the derivative of this thermodynamic entropy with respect to temperature. Now I can use the chain rule and find the derivative with respect to beta. So then I will need to do this, right? This becomes derivative of beta with respect to t. Beta, remember, is my unknown. I want to find out my beta. I will take the derivative of this with respect to beta because it's expressed in terms of beta. This becomes kb I can just put this kb outside. Now I need to find the derivative of this thing with respect to beta. So log of z. Z is my trace of E minus beta h. All of this is z, right? This is z. So I'm finding the derivative with respect of log of z. So this will become 1 over z correct? Now what is this thing equal to? If I just going to put what I've written in yellow, the derivative equals trace of e minus beta h, which is z itself. The derivative of exponent is the exponent itself multiplied by the derivative of what's in the exponent minus beta a trace of h. So this becomes minus this thing, right? Is there a term that I'm missing over here? Oh, actually, sorry. When I find out the derivative with respect to beta, so there's an e, but there's also this term, beta d e by dt. Sorry, d e by d beta. This term as well. So, plus beta d e by db. This is an average of e. This is 1 over z multiplied by minus z average of e, which becomes minus e. This just goes away. Finally, the derivative of the thermodynamic entropy with respect to temperature becomes Kb beta d average value of E dt. Right? I just unwind the chain rule. And when I unwind the chain rule, I then look at what I've written in the big box over there. This must equal 1 over T and now lo and behold, I know that my beta equals 1 over Kb T. It's the Boltzmann factor. So using thermodynamical principles, I can find out both the Lagrange multipliers. The first Lagrange multiplier lambda was found out from a constraint on the density matrix, and the second Lagrange multiplier could be invoked only by some knowledge of thermodynamics. Hence the equilibrium density matrix is given by E to the power minus beta h over trace of this thing, which is the partition function. And this equilibrium density matrix has maximal entropy at a given temperature and a given energy and a given average energy. Alright, so now I would like to move on to the idea of information. I would like to discuss the idea which is at the heart of all communication, that's the idea of mutual information. कोई equilibrium density matrices की समझ आ गई है कि नहीं? सच्ची बात बताऊं, अगर आप होमवर्क 4 कर लें जो कि डेंसिटी मैट्रिसेस के इर्द गिर्द घूमता है, you'll get a hang of it. Need to do that homework. There's no escape from that. So the idea of mutual information is the following. Suppose I were to make, let's come up with an event A has some entropy, event B has some entropy, and I add these entropies, and from this I subtract the entropy of the joint event of A and B happening. So now this might seem just boring, but this is really at the heart of the noisy coding theorem of information theory. So let's find out what this thing means. Let's see. And we can also represent this pictorially. HA is given by the sum of PA log of PA, the minus sign. That's my HA. My HB is, let's use different index, PBJ log of PBJ. And this minus sign turns into a plus sign, plus the joint probability of AI and BJ occurring log of PAI BJ. So this is what this sum HA plus HB minus H joint probability of A and B turns out to be. 3 sigmas, big sigmas. So this object here, PAI, can I represent PAI as, this is our very first lecture, as PAI comma BJ sum over all J's. Correct? And we can do a similar thing over here. And when we are to do this, we get minus sigma IAJ PAI BJ log of PAI minus sigma IJ PAI BJ log of PBJ plus PAI BJ log of PAI all of this can be written as sum of ij. Let's take this common, PAI BJ log of PAI BJ divided by PAI PBJ. I hope you agree with me. Correct? Now what is this thing? Recall in previous lecture, relative entropy. This is the relative entropy between two probability distribution functions. And that relative entropy is the relative entropy between one of the functions is PAI BJ, this thing in the numerator, and the other is, remember our symbolism for relative entropy, the other is the product of these two single probability distribution functions. Now what is the important property of relative entropies, which we proved in the previous lecture? From the up it's unbounded, and from the bottom its minimum value is 0. And that minimum value 0 exists when the two probability distribution functions are identical. So HA plus HB minus HAB is 0 and above. This thing has to be 0 or above. And it's 0 only when the two probability distribution functions at stake are identical, which means this equals this. And when would this joint probability distribution function equal the product of the singles? When the two events are independent. When the two events are independent, does HA plus HB equal HAB? Right? This is when the two events are totally independent. A and B are independent. Otherwise, HA plus HB is greater than HAB. Now let's represent this in a probabilistic Venn diagram. So this quantity HA plus HB minus HAB is so profound that it's given a special name. It's called the mutual information of A and B. So this thing over here is so profound in communication theory, depends upon A is at Alice's side, the sender side, and B is at the receiver side. So one would like to find out if B measures something, can she tell or can he tell what Alice has sent out as a message? So this is such a profound expression, it's given a special name, the mutual entropy or the mutual information, and the symbol for this is A colon B. If I were to represent this in a Venn diagram, where all of these concepts come together, is I have a space for A, event A, I have a space for event B, now this is, all of this is information content in this blob is HA. The information content in all of this blob all of this blob, all of it is HB. Right? And whatever you see, the sum of these blobs is sum of these, right? So let me draw the sum of these. The sum of these blobs is H, A, comma B. The joint probability of A and B, the joint information content. And what's in between, the overlap, is the mutual information between A and B. And this mutual information of A and B is HA, all of this, plus all of this, minus all of this. Because there's a double counting that takes place over here. Right? So that's how we diagrammatically represent the idea of mutual information. The last thing I would like to mention before we break break this class is the following. So really the mutual information tells us about the correlation between two events A and B. The correlation between two probability distribution functions. Okay. The last thing I'd like to point out is conditional entropy. And then we'll be done. Then we can move on to communication theory in the next class. In the next class, by the way, our very dear Abdullah is going to walk you through homework number 3. Some real examples in class. Just trying to do everything I can to ensure that the homeworks are important. The last thing I would like to mention, the last 5 minutes, is the idea of a conditional entropy. Just a couple of minutes perhaps. And I would like to ask you what's happening. It's also related to our Venn diagram. If I were to take the probability, joint probability of A and Bj, what would this look like in terms of the Bayes rule? How can I express a joint probability in terms of conditional probabilities? What's the Bayes rule? That represents a joint probability in terms of conditional probabilities. Ai given Bj multiplied with the probabilities of all Bj's. Correct? This is the Bayes rule, one form of the Bayes rule. Now can I express, now you already know that how do we represent entropies in terms of probabilities. When probabilities multiply, information adds up, entropies add up. So if I were to write down the entropy with respect to this joint probability, that will look like HAB. Equal to, let's call the probability that looks like, that corresponds to this joint probability. Any probability you take, multiply the probability with the log of that probability, sum up with the minus sign, it becomes an information content. So I can write this as H A given B. This is a conditional entropy. Conditional entropy of the event A given that the event B has occurred. So if the event B has occurred, how much there is more to be known about A? What's the information content in A that's left over? This is what the conditional entropy means. Now the entropy corresponding to this single is HB. Now what do I put here? Do I put a multiplication or a summation? Summation, because the entropy has a log in it. So this is how we define the conditional entropy. The conditional entropy A given B is the joint probability minus HB, the single probability, or the other way around, HB given A is HAB minus HA. And you can also express this in terms of the mutual information. You just look at the definition of mutual information, put it in here. Right? So, of course, you can express this in terms of mutual information as well. Now, what does this mean? Let's look at our Venn diagram. This is A, this is B. The conditional entropy of A given B is all of this minus HB. So if you were to know B, if you were to know the information content in B, how much information in A is left to be discovered? That's this much. The uncertainty in A is this much. The information content in A is this much. And this is what this thing means, right? All of this minus all of HB, you left with this. This is the conditional entropy of A given B, what I've represented in yellow. Likewise, I can find the conditional entropy of B given A. Now, what is all of this good for? Mutual information, singles entropy, Shannon entropy, von Neumann entropy, conditional entropy, relative entropies. All of this is basic definitional work. We're going to use all of this in communication theory. If Alice sends quantum information over to Bob, how many bits does she need? How many resources does she need? And if there is noise that is attacking the channel, how is that going to affect Bob's outcome? And how reliably can Bob figure out what Alice has said? Now, I would like to end up with one sentence. Just one quick kind of task I would like to give you. I'm going to write something on the blackboard. And I would like you to just see what I'm going to write. Sorry, RSS isn't what comes to your mind, but RSS. Now this is an English sentence. I've missed out certain vowels when I've written these words. So I've skipped the vowels. Is it possible for you to read what this means?
Grass, green, blue.
Grass, green, blue.
And last one.
What's this?
Red.
Red. Grass is green. What is red? Roses are red. Lilies are blue, right? Roses are red, lilies are blue, grass is green. So I missed out the vowels. Still, you're able to decipher to an extent what this message means. So the vowels are kind of extra. Okay? So there was some redundancy in the message that was transmitted. Redundancy means you put in something extra so that but that extra is not really needed. So how can you compress information? You want to compress information. When you want to transmit information, you want to compress it. Okay? So this is an idea of redundancy. Now if this message is transmitted in an optimal fashion from Alice to Bob G.
Isn't you a vowel?
Okay, that's fine, you can keep 1 and 2. That's fine. So if now this message is transmitted, the redundancy is removed, it's fine. So you compress the data, you've compressed the amount of information that is required, you compressed or reduced the power requirement, etc. But what if noise takes place? In the channel there is some noise, some letters are flipped. So from one alphabet they get to another alphabet. So if I make some random changes, say R, P, S, X, D, L, F, Q, B, L, R, G, P, F, S, R, G, Q. Now it's impossible for you to read this message. So redundancy is added so that your message becomes robust against noise. There's a trade-off. So if you want robustness against noise, you cannot compress your data. Redundancy is added so that you have robustness against noise. So even if noise, so if I were to write the full sentence, roses are red with all the vowels, and some of the letters then got misspelled, like a child writing in his or her notebook, then you would still be able to decipher the message. So redundancy is built in so that your message is protected against noise, but then you need more resources. So all of this is now the task of information theory to find out the resource question. Information now is physical. How much resources do you need? Information is not just in the air, it requires physicality, physical resources. Now in the next lectures, from next week onwards, we're going to find out what those physical resources are, what are the relevant theorems, And then we look at quantum key distribution, one of the hallmarks of quantum communication. Thank you.